Welcome to the 2020 Informs OR and Analytics Student Team Competition. I'm delighted to introduce the finalist presentation by the team from Urzane University.
Thank you, Mrs. Cryan, for introducing us. So we are 6 industrial undergraduate students that are good friends for half a decade, and we're so honored to be in your presence. So we are ready whenever you are. So when you want, we can start the presentation.
Yep, go right ahead.
Should I start it now?
Yes, go ahead. Yep.
Okay, I'm starting my own timer as well.
Okay.
Esteemed judges and guests, it's an honor to be in your presence. We are the Özyeğin University team from Turkey. We are a team of 6 industrial engineering students that are good friends for half a decade. In the problem, Jelly Bean is the hypothetical product with different attributes that can be produced in 5 production plants with similar infrastructures and different rates and cost. There is essential deterministic demand to be allocated and transportation option before production. In the production system, the respective drums can only have materials of the following attributes during a transfer. Due to weights of the drums, we have assumed that after attaching a drum to a process, it can only be detached once the material in it is fully transferred. In our simulation model, we have developed some heuristics for flavoring and packaging cues. And due to stochastic nature of pharmaceutical supply chain, which can be observed in COVID-19 case that we're all facing, we gave great importance to time by expressing it as a cost in our objective function.
We made statistical inferences with the initial information to gain an insight. First, we found that amount of total raw material is greater than amount of total demand. Therefore, we deduced that we should expect excess production. Second, we fit a normal distribution to the given historical process rates to use them in our simulation model. Third, we introduce a crucial parameter for our solution approach, cycle length. That is the time that an entity spends in a production facility from classifier to being an SKU. In the first table, we calculated the time required for each facility to process its raw materials without considering the waiting times. Our aim here is to have an insight about the overall status of each site. In the second table, we calculated production time for each facility if total amount of raw materials are divided equally to 5 sites. Our purpose was to determine the fastest and slowest sites, which are Omaha and Springfield, respectively. For our solution approach, we created a mathematical model and a simulation model. The aim of the mathematical model is to determine the allocation of the central demand to each site and transshipment of the raw materials between sites. Moreover, the discrete event simulation model is used to estimate the cycle length parameters realistically. The link between our mathematical model and simulation model is this cycle length. At the beginning, we estimate cycle length values according to given data without considering the waiting times and use them as parameters in the mathematical model. The outputs of the mathematical model used in simulation runs. Each simulation run gives us realistic cycle lengths in which waiting times and delays are considered. After standardization, we use these new cycle lengths in the mathematical model. And this transaction continues iteratively until total cost converges to a constant level and the percentage of demand satisfied increases. This process is where parameter tuning, which resembles a machine learning algorithm, occurs. Finally, I would like to emphasize that our solution method is a compound heuristic. That is the combination of a constructive heuristic and an improvement heuristic with machine learning. In this slide, you can see the decision variables of our mathematical model. The most significant ones are T, which represents the transportation amount, and X, representing the amount of allocated demand. The objective function minimizes the cost. First part represents the monetary cost of total time spent in production. Here, alpha coefficient is the cost of spending a minute in the system. Second part is the cost of production of the allocated demand. Third part represents the transportation cost. And finally, we have a demand separation cost that helps us to allocate the same attributed demands to the same site to increase efficiency. Here, gamma coefficient is the monetary cost of demand separation. Our first constraint is the track capacity constraint. Constraint 2 and 3 are shipment and capacity constraints for full and semi-full drums. Constraint 4 and 5 are the equivalent of the previous constraints for empty drums. Constraint 6 and 7 links the transportation decision variable with its binary. Constraint 8 allows an empty drum to receive only one type of color. Constraint 9 and 10 establish a relation between binary variables. Constraint 11 makes sure that after the transshipment, there is sufficient amount of raw material for the allocated demand. Constraint 12 prevents the model from allocating problematic part of the aggregated demand with the coefficient beta, which is equal to 85%. Constraint 13 helps the model to find the maximum duration of production among all sites. Here, parameter tuning occurs. 14th constraint provides justification for a binary variable. 15th constraint prevents an allocated amount from being less than the smallest amount in the given demand data, which is 519. And the rest is non-negativity, integer, and binary constraints. Finally, our mathematical model assumes that raw material is allocated according to beta. Also, an RMI drum making a transshipment cannot receive any material.
So in the simulation model, we have analyzed two different RMI queuing policies. First policy processes the lowered number drum earlier, whereas the second policy processes the RMI drum that contains the color that is most frequent in the demand earlier. Our classifier algorithm first checks if there is an RMI drum attached to the classifier. If an RMI drum is not attached, it takes a drum. Once there is an RMI drum attached, the algorithm checks if there are 5 available PFI drums at each end of the classifier. If there are not enough PFI drums, the algorithm attaches idle PFI drums starting from lower numbered drum. Once there are 5 PFI drums, the algorithm checks the attributes and capacity of all attached drums. If there is a mismatch in RMI and PFI drums, the PFI drums are released and sent to the flavoring queue. Else, the material can be transferred. In the flavoring algorithm, it first checks if there is a PI drum attached. If not, attach the lower number idle PI drum to the process. Then, if the PI drum has material in it, the algorithm tries to find a PFI drum in the queue that has the same attributes which also exist in the allocated demand of the facility. If such a PFI drum exists, the drum is processed. Else, the PI drum is released and sent to the packaging queue. If the attached PI drum is empty, the algorithm tries to find a PFI drum that can be flavored with the last flavor according to the allocated demand. Else, the algorithm tries to match the last flavor according to the other 4 facilities' demand. If still there is no such PFI drum, a random demand is processed. And all of these heuristics are to minimize time penalties. Our packaging algorithm tries to produce first the demand allocated to the facility, else the demand allocated to the other 4 facilities. If there is no such PI drum, then the material is transformed to a box. And for every process, boxing line has priority for packaging. We have introduced 2 performance matrices. Overall demand satisfaction measures the percentage of overall demand satisfied and can be 0% or 100% for a demand, whereas overall quantity satisfaction measures the percentage of overall quantity satisfied. For example, demand is 500 here, and when the production is 400, we say that demand satisfaction is 0% since production is smaller than the demand, and the quantity satisfaction is 80%. The graph shows the response of parameters to our performance matrices. Alpha is the cost of unit time of producing per pound demand. First, we have calculated the total demand production cost, the total time, and found alpha to be 80. Importance of time increases with increase in alpha. For values smaller than 80, the production times exceed 6 months, and for values greater than 80, the quantity satisfaction is decreasing with overimportance given to time and cost is increasing. Therefore, we have selected alpha in our mathematical model to be 80. Beta value is the minimum percentage of overall demand allocated and used to eliminate outlier demands that would cause drum inefficiencies. As we have decreased the beta value with the help of our heuristics, the satisfaction increase. To not decrease the importance of the mathematical model decisions, we have selected beta to be 85%. Finally, gamma is the cost of same attributed demand separation. We aim to group similar attributed demands as much as possible to increase drum efficiencies. There is a significant difference between setting gamma to 0 and 100, but for computational purposes, we have set gamma to be 100. We have tested lowered numbers first and color-based RMI ordering policies. The graph shows the response of satisfaction percentages and total cost to parameter tuning iterations. RMI ordering policy has minimal effect on performance, and since the initial cost of color-based ordering is smaller, we have chosen that as our queuing policy. Since the maximum satisfaction percentages are observed in iteration 2 and cost converges at that point, we have tuned the cycle length parameters for 2 times.
In the table below, we observe the percentage of RMI after transshipment and allocated demands for each site. And as you can see, the summation of the percentages of the demand allocated is equal to 85%, which is the value of the beta coefficient. And these are transportation amounts between sites, production amounts for each site, initial estimates for the production times, real production times obtained from the simulation, and the differences between the last two. Additionally, I want to point out that the smallest difference occurred in the Springfield plant, which is also the slowest plant. And the largest difference occurred in the Green Bay plant, which has the maximum amount of access time. Therefore, this is a justification of our model's capabilities. Moreover, I would like to emphasize that we processed all raw material in less than 6 months. You can see the access time in months of each site in the second row of the slide. And our overall quantity satisfaction rate is approximately 84%. The classifier utilizations are as follows. When we look at the flavoring utilizations and their average queue lengths, they are all greater than 99%. The packaging utilizations and their average queue lengths are as follows. Due to the intensity in the flavoring process, packaging utilizations are smaller. This also causes inefficiency in PI drum usages. In Green Bay and Springfield, there are 9 PI drums that were never used. The bottleneck in every site is detected to be flavoring.
Then we have extended the problem and took the last simulation run by lowering the PFI and PI drum capacities around 50%. The increase in time are relatively smaller to increase in performance. In all of the facilities, the production of allocated demand has increased, whereas the production of other facility demand and random demand has decreased. Since the increase in allocated demand production is more, the overall satisfaction increased by 7%. Also, there is a cost saving around $29,000 since there is a decrease in random demand produced because the random demand was trying to minimize time and was not giving an importance to cost. And when we apply this change, the utilizations change on average 1.5%. In conclusion, we have built a flexible solution technique that is adjustable to alternative scenarios. The importance of time, percentage of demand to be allocated, and even drum capacities can be set with parameters. All of the raw material is processed before the 6-month time period, and the quantity satisfaction is 91%. With our extension, Green Bay has 4, Omaha has 2, and Springfield has 1 month of idle time, and with procurement, the demand can still be 100% satisfied before the desired time limit. Excess products can be stored in inventory to satisfy a possible stochastic demand, which is the real demand nature of pharmaceutical supply chain, or can be sold to customers with a penalty, only if the packaging type is different. For each site, flavoring is the bottleneck, and Green Bay needs more RMI drums. And Green Bay and Springfield has 9 PFI drums that has been never used, and they can be utilized in other ways. Since when the drums are attached to a process, they can only be detached once the material in it is fully finished. Decreasing the PFI and PI drum capacities to a level can increase flexibility and satisfaction with minimal increase in time. Decreasing the sizes and increasing the quantities of the drums would allow the factories to achieve 100% demand satisfaction with the existing raw material. The production site should be able to process online data and make the production decisions accordingly. Real-time information network between sites is essential for implementing our dynamic model. As Industry 4.0 principles suggest, there should be machine-to-machine communication along sites, and it will facilitate more accurate and digitalized decisions. Finally, after digitalization of data, our model aims to apply digitalization of decision-making to the existing production system. Thank you for your undivided attention, and if you have any questions, we are happy to answer.
Excellent, wonderful. Thank you very much. And that's a great last slide with jelly beans.
Thank you,
And
Ryan.
Dr. Burge will, and the judges will now ask you folks some questions. And you might want to all take your mics off, unmute yourselves. You can decide who will answer which question when it comes up.
Okay, thank you for your presentation. We have a few questions. I'll start with Willem.
Thank you, John. Thank you, team, for a great presentation and putting in some hard work. It really shows, I think, in the slides that you presented. I very much liked your approach. You took a non-traditional approach, if I may say, by developing this heuristic approach. I do have a question about the cycle length parameter that you mentioned. You didn't go into too much detail in the presentation, but I was wondering if you can maybe clarify a little bit more how you update this cycle parameter during the iterative process.
Thank you for your question, Professor. Let me go to the slide where we have our general approach, and Ahmet will answer this question for you.
Okay. Initially, the cycle lengths that were given by the buyer are not includes the interruptions and waiting times in the queue. And thanks to our simulation model, we can see the detailed explanation of the times. Actually, we are reaching the real time that producing 1 pound of the products from classifier to the end of the packaging. And thanks to that, at the end of each iteration, we are updating our cycle length according to if that cycle length updated before in the previous iterations, we are taking the mean of both of the cycle lengths. And if it is not updated before, we are updating just replacing with the new one to the given one from the buyer.
Interesting. Thank you very much. And a related question to this is, since you do not have an exact method, which I completely understand, of course, do you have any idea how far from optimality you are? Is there a way to measure this? Can your costs be further reduced?
Actually, according to our mathematical model, we can say that our optimality gap is around 3 out of 1,000, I think. But in this applying to the simulation model might be caused, and how can I say? I couldn't say the correct word. Sorry for my English.
No problem, no problem. But you mean to say that that you might use the lower bound of the linear programming relaxation?
Yeah, actually upper bound. It's upper bound because the complexity of the problem is very huge, and we are using too much thousands of the decision variables, and it might be computational very complex model. In order to avoid this, we decide the upper bound of the 3 out of 1,000.
Thank you very much. Great work.
Okay, thanks, Willem. Question from Shrikant.
Thank you, Dr. Burge. I think this is a great presentation, and sitting through your presentation, it was very clear that you understood the problem statement and how you translated and how you explained the analysis. The question I had is, as you iterate between the mathematical model and the simulation model, what is the stopping criteria?
Thank you for this question, Professor. So Rüzgar will answer this question for you.
Thank you.
We calculate the accuracy after the all simulation part, and when the accuracy is stabilizing, we stop the simulation. And also we have 5 facilities, and each iteration we updated 1 facility cycle length. So 6 iteration in total is enough for us.
So I have something to add as well. So we set the maximum number of iterations to 7 because there are 5 facilities. So we assume that when we are updating the cycle length in our simulation model, like it almost reached to all of the it considers all of the possibilities. And we have observed that after iteration 2, since our satisfaction has achieved to its peak point and the cost converges at that point, we have iterated twice. So this is our stopping condition, and we have verified it with our sensitivity analysis, which is here. Let me show it. So as we iterate, this one iteration is like taking cycle length and putting it to simulation and taking back to mathematical model. And as we iterate over this, the importance of time increases. So as importance of time increases, as we iterate, the idle months start to decrease. But at this peak point, we have achieved that there is the maximum satisfaction and the time constraints are more bounded. So therefore, we have set the iteration number as 2 and cost converged at that point. I hope we were able to answer.
Yep, thank you.
Okay, thanks, Shrikant. We have a question from Mark Mickelton.
Hi there. Great presentation. 2 related questions. One, your mathematical optimization implicitly tries to predict what the total production time would be, but your simulation model will actually get that right. How close does the mathematical optimization model kind of track what the simulation model says in terms of production time?
Thank you for this question, Professor. Again, Ahmet will answer your question.
Actually, Ali, could you open the slide that we show the initial and the final times that we estimated?
Yes, of course. Here.
Actually, the initial ones are that we want to obtain from the according to our mathematical models results that assigned to the demands that are assigned to the sites. And after that point, we can see that the blue ones shows the simulation models times, and the green ones are the difference between them.
Okay, so it was there. I missed it. My related question is, suppose that you wanted not just to get within the 6 months time, but you wanted to kind of reduce the longest make span, the longest production time. Would your model be able to be manipulated for doing that? Because that might reduce the overall risk.
I can answer it if you want, my teammates. So if I'm right, you're asking if we can find the point where all of the times are bounded as much as possible.
Yes.
So actually, we can do it because we have a data set in this slide. So let me open it. In our sensitivity analysis, we also know how time behaves to our iteration. So from that behavior, I think to our iteration and time, I believe we can get that information as well to reduce the possible risks.
Okay, thank you.
This answers your question.
Yep.
Okay, well, thank you for your presentation. I don't see any other questions, so I want to thank you for taking time to tell us about what you've done for this prize, and I'll turn it back to Terry.